Okay folks, this is the last video for our pre-work for section 2.6 on the topic of continuity. And in this section we're going to look at what's called the intermediate value theorem. This is the first of the named theorems in this class. So in a calculus class, if they name the theorems, there's probably something important about them. This is called the intermediate value theorem. Okay. What does the intermediate value theorem say? Well, as you're getting comfortable with reading theorems, what I would encourage you to do is start to separate everything that's said into the conditions that need to be met for the result to occur, and then what is the result itself. So read this over. Pause the video, read it over. So what is the result from this? The result is, in fact, it's sometimes called an existence theorem. It guarantees that there is some x star, some number in the domain, specifically in the interior of the domain, so when we plug it into the function, it outputs n. That's what we're hoping to guarantee. Okay. What are the conditions that need to be met? Well, the conditions that need to be met are these. Suppose f is continuous, so we need a continuous function, on a closed interval, okay, so we need a closed interval, AB, with the y value of one of them less than the y value of the other one. Then for any choice of n, as long as n is between those two y values, then we are guaranteed that there exists an x star so that this expression happens. Okay. That's a lot of information, and this one takes a little bit to unpack. Let's see what we can do here. Okay, let's go ahead and give the let's go ahead and just set up a picture that might help us keep track of things a little bit better. So let's see here. Here's our x-axis. Here's our f of x-axis. And let's start running through. We'll fill in the continuity of the function here in just a second. But we've got a closed interval. Closed interval on AB. And we've got f of a, the y value. We plug a into the function. Here's f of a. This y value needs to be below f of b, so the other point has to be somewhere up here. That way, notice f of a is below f of b. We don't actually need f of a to be below f of b, but we need to make some sort of statement like this at some point, so it's easier to pick. It's easy to pick, let's say the left value is below the right value. We could have flip-flopped those. Okay, so the intermediate value theorem says now pick. In fact, this is why it's called the intermediate value theorem. Now pick some n in between these two y values. Maybe this n right here. I'm going to erase that. Or if you like, this n right here. It doesn't matter. It says for any choice of n, as long as n is between those two y values. So I don't know, let's go with that one right here. There is guaranteed to be an x value, where? On the interior. Let's see here, I'm running out of colors. On the interior between A and B, somewhere in between A and B, so when we plug that x star value into the function, it will output the number n. Okay? We're guaranteed that this is going to happen. Well, we don't know what our function looks like. Let's just come up with some function. We could go something like that. Okay? Or, if you like, I'm just going to change it. We could do something like that. It doesn't matter. As long as the function f that I draw, as long as it's what? Continuous on this closed interval, like I did here, then for any choice of n, we pick this n here, we're guaranteed to find some x star. What do I mean by x star? Well, it's some number that when I plug it into the function, it outputs an n. Let's see here. If I go ahead and, let's go ahead and extend this over a little bit, and it's kind of a little cluttered, but we'll do that anyway. This would be my x star. This number, I'm trying to point to this y value, this x value right here. This number, if I plug it into the function f, what does it output? It outputs n. Was I guaranteed that there was an x star, that when I plugged it into the function it would output n? Yes, I was, by the intermediate value theorem. Now, it's important to realize that this isn't saying that's unique to just this graph that I just drew. I could draw some other function on the interval from A to B. And as long as I draw it continuous, and as long as I make sure the left value is below the right value, let's see, we could do something like this. Okay. Then, let's see here, here's our f of a, and better extend that up a little bit. Here's our f of b. As long as I pick some n value that's in between those two, we could pick this n value here, I'm guaranteed to find an x value that when I plug x star, that x star into the function, what does it output? It outputs a y value of n. What if I picked a different n? Erasing this. What if I picked a different n? Well, I don't know. We could pick maybe this n right here. Do I still have an x value that when I input x into the function, that x star into the function, it outputs an n? Sure I do. How about this one right here? Plug this into the function. What does it output? N. In this case, there's actually a couple of them, so maybe we ought to put subscripts on them. There's x1 star, here's x2 star, here's x3 star. When I plug these into the function, I'm guaranteed to find these x stars so that when I plug them into the function, they output an n. There is no way I could draw a continuous function between a and b without at least one y value of that function passing through n. Try it, I dare you. So, what does the intermediate value theorem say? It says for any intermediate value choice between the two y values of the endpoints, there is always a point on the graph that has that as the y value, no matter how you draw that graph, as long as what? And this is the crux of it, as long as that function is continuous. Okay, so I'd like you to do number 22 on your own. Give an example of function where the intermediate value theorem breaks down when f is discontinuous. Okay, so see if you can come up with that. It might take a little bit of thinking, but give it a shot. Okay, what do I want to say about the intermediate value theorem? Well, sometimes the intermediate value theorem doesn't seem all that impressive because we encounter it in our everyday world all the time. So here's a statement of the intermediate value theorem that you would expect. Okay, so let's say we've got a car's velocity. Well, a car can't change velocity from 60 miles per hour to 65 miles per hour without going, say, pick some number between 60 and 65, like 62, at some point in time. That the car can't jump from going 60 miles per hour to 65 miles per hour. It has to pass through all values in between, all intermediate values between 60 and 65. It has to take on all those values. Okay? Specifically, in this case, the intermediate value is 62. At some point, the car has to be going 62 miles per hour. Why is that? Well, at the heart of this is the fact that the motion that you and I experience on the macroscopic level, the motion that we experience in the world around us is a continuous motion. Because motion is continuous, we know that this intermediate value theorem must apply. Now, kind of an interesting thing is not all types of motion is continuous, and in fact, Einstein showed that light can behave either like a continuous function or a discrete function, meaning behaving like a particle, in which case there would be discontinuities, which is why at the subatomic level, interesting things happen with regards to the intermediate value theorem. You encounter things such as quantum tunneling, where a particle goes from point A to point B. It'll pass between those. It'll go from point A to point B without passing, there might be a wall here, without passing all points in between. But that's because the intermediate value theorem doesn't apply at the subatomic level in all cases. All right, so let's look at one more example. In question 24 here, we're asked to show there is a root to this equation on the interval from 1 to 2. Okay? So we want to guarantee, by root we mean an x value that when we plug it into this expression, it outputs 0. So let's go ahead and give ourselves a function so we can give a name to everything. So let's say f of x is equal to 4x cubed minus 6x squared plus 3x minus 2. Okay? I'm saying prove there's a 0 to f between x equals 1 and x equals 2. Okay. Well, how could we do so? Well, we could try a few things, but we're being asked, this section's about using the intermediate value theorem. So let's go ahead and see what we can do here. Let's first say that f is continuous where? Well, first of all, it's a polynomial function, so it's continuous from minus infinity to infinity, right? So specifically, even though this function is continuous on the entire real line, why? Because it's a polynomial. We can be a little more specific, and we can say that it's continuous between 1 and 2. What am I trying to do? I'm running through the requirements of the intermediate value theorem. I need a continuous function. Well, our function is continuous on the closed interval. Okay, so I've just given ourselves a closed interval between 1 and 2. Okay, now let's see what f of 1 is. Well, f of 1, if I plug a 1 into this function, let's see, that would be 4, and minus 6 is minus 2, plus 3 is positive 1, minus 2. We get f of 1 equals negative 1. Let's plug in 2. When we plug in 2, let's see here, we get 32 minus 24 is 8, plus 6 is 14, minus 2, I believe we get 12. So what have we just shown now? Well, again, I'm running through these requirements of the intermediate value theorem. I've got a continuous function between 1 and 2, and we just showed that f of 1 was less than f of 2, right? What was f of 1? F of 1 was negative 1. What was f of 2? It was 12. Okay, so we just met the conditions of the intermediate value theorem up till now. Now pick any number in between f of 1 and f of 2. Well, although the intermediate value theorem applies for any value between negative 1 and 12, the number between negative 1 and 12 that we're most interested in is 0. So here, pick n equal to 0. By the intermediate value theorem, we are guaranteed an x value contained where? Contained in the interval between 1 and 2, so that f of x star equals 0. And there's our proof. It relies on the intermediate value theorem. Okay. Let's actually, we'll leave it at that. If you wanted to plot these 2 points, I'm not going to draw the whole graph. You could plug it into an equation solver or something. But notice we plugged in 1, we got out negative 1. That was 0 pair 1 comma negative 1. And when we plugged in 2, there's 1, there's 2. When we plugged in 2, we got out the 0 pair 2 comma 12. And what does the intermediate value theorem say? It says no matter what this function looks like, because I know it's continuous, there's got to be some point where it crosses the x-axis. There's no way I can go from here to here in a continuous manner without crossing the x-axis at some point. So there's an application of the intermediate value theorem.